Okay, so for this chapter, we'll be discussing mainly the colligative properties of solutions. But before we do that, we have to go through some preliminaries so that you are reminded of some things that you would have learned before in your freshman general chemistry 1 or introductory chemistry courses. So what we're going to talk about firstly are the different types of solutions. And this is something you should have learned early, as I said before. The definition of a solution, of course, is a homogeneous mixture of two or more substances. And a solution is made up of basically two components. You have the solute and you have the solvent. And you can have more than one solute actually, but typically you have only one solvent. So the solute is or are the substance or substances present in small amounts in the solution, while the solvent is a substance that is present in larger amounts. Now, as you can see in the table below, there are the possibilities of the components of a solution being of different or the same phases. So, for example, you can have a mixture of two or more gases. That would be a solution, right, which would be a gaseous solution. And a good example of that would be the air we breathe, all right? Now, in other instances, you can have, for example, a gas dissolved in a liquid. For example, carbon dioxide dissolved in water. You can also have, believe it or not, a gas dissolved in a solid. Now, this is something you don't see every day, but this is something that can actually be created in the lab. And a good example of this would be hydrogen gas dissolved in palladium. And this is a specialized reagent that is used to carry out certain organic reactions. We can also, of course, have a liquid dissolved in a liquid. So there are many examples of that we can see from our everyday experiences, such as ethanol in water. Um, Again, another example that is very common, solid dissolved in liquid. And a good example of this would be sodium chloride in water. You can also have sugar dissolved in water as another example. And then the final example of a solution where you have a solid dissolved in a solid. This is also very common, where you have a mixture of, let's say, two metals to form what we know now, what we call an alloy, such as copper and zinc and tin and lead. All right, so these are all different examples of solutions. Okay, so let's delve deeper into the behavior and characteristics of solution. Now, we can have in a particular solution different proportions of the different components. And as such, this gives rise to the concept of what we call a saturated solution, where we have a solution where it has the maximum amount of solute that will dissolve in a given amount of solvent at a specific temperature, right? So basically what this means is that in a saturated solution, it contains a certain amount of solute and it cannot basically contain any more at the particular temperature. Then we have what is known as an unsaturated solution, which is basically the opposite, where the amount of solute present for a given amount of solvent is below the saturation level. All right. And then we have a very unstable system known as a supersaturated solution. And in this case, this particular solution actually contains more solute than is present in a saturated solution that we described earlier. And let me emphasize again that this is very unstable. Um, it can exist, but if you do anything to it, almost immediately you'll have solid or the solute coming out of solution. And this is seen, for example, if you have a supersaturated solution of sodium acetate, and if you add just one crystal of sodium acetate to this particular solution, these pictures demonstrate exactly what will happen. So the picture on the left represents or is a supersaturated solution of sodium acetate. And what this person did was just add one crystal of the same sodium acetate solute, and you have the spontaneous formation of solid sodium acetate coming out of solution. All right, and that sodium acetate will come out of solution until the concentration of sodium acetate in the solution is at the saturation level. All right, and we can do this with other solutes as well. Okay, so let's look at the thermochemistry or the thermodynamics involved when you have the formation of a solution from its solvent and solute. So we're assuming in this particular example, and it's a hypothetical example, that we have one solute that you're dissolving in a solvent. So over here, we have our solvent molecules. And in order for the solution to form, you need to have a separation of the solvent molecules because, of course, there are forces that will exist between the solvent molecules. So, therefore, a certain amount of heat would have to be absorbed or delivered to the solvent to separate the molecules. So, we call that delta H1. That's step one. And then over here, step two, similar thing will happen separation of the solute molecules. So therefore, the amount of heat required for that would be delta H2, and you end up with the separated solute molecules. And then we have step three, where you have the solute dissolving in a solvent. And of course, as a result of the dissolution, there will be forces of attraction between the solute and the solvent molecules. And that is typically an exothermic process represented by delta H3. So therefore, using Hess's law, which is a law you should have learned in Chem 1, we can write down that the enthalpy change for the solution formation would be equal to delta H1 plus delta H2 plus delta H3. So what you'll notice here, as I said before, because delta H1 and delta H2 involves energy being absorbed, these are endothermic processes. So therefore, delta H1 and delta H2 is going to be positive. And because we have forces of attraction being formed between the solute and solvent molecules to form the solution, then delta H3 would be negative because it's an exothermic process. So basically, we have these two terms which are positive and the delta H3 which is negative, and therefore the overall sign of delta H1 is dependent on the magnitude collectively of delta H1 and delta H2 compared to delta H3. So in other words, if delta H1 and delta H2 is large and positive and delta H3 is smaller in magnitude and negative, then the delta H solution would be positive and therefore it would be an endothermic process. On the other hand, if delta H1 and delta H2 are small but positive and delta H3 is large and negative, then delta H solution would be negative, which means that the dissolution process would be exothermic. Okay, so a general rule of thumb that applies when it comes to determining what will dissolve in what particular solute or solvent, what solute will be dissolved in what particular solvent, is a like dissolves like. And basically what this means is that two substances that have similar intermolecular forces are likely to be soluble in each other. So basically nonpolar molecules are essentially, in most cases, soluble in nonpolar solvents, such as carbon tetrachloride in benzene. On the other hand, polar molecules would be soluble in polar solvents, such as methanol in water. And what you'll find also is that ionic compounds tend to be more soluble in polar solvents, such as sodium chloride, which is soluble in both ammonia and water. Okay, let's talk about concentration. So, of course, this term is something you should have met before in your introductory chemistry or your general chemistry 1 courses. And the definition of concentration is shown here. It is basically the amount of solute present in a given amount of solvent or solution. And there are different ways of expressing concentration. One way is by what we call percent by mass, where we simply take the mass of the solute and divide it by the total sum of the mass of the solution and multiply that by 100%. So that is called percent by mass. You can also have what is known as a mole fraction. This is something you should have met in General Chemistry 1 when we discuss gases, but of course we can also apply it to pretty much any mixture. So the mole fraction of a component A in a mixture will be equal to the moles of that component divided by the sum of all the components in that mixture. Another way, I should say, of expressing concentration is again something you should have met before. It's called molarity, symbolized by the uppercase M. And molarity by definition is the moles of solute divided by liters of solution. Now there's another term which you may not have met before, and it sounds similar to molarity, but it's different. It's called molality, and it is symbolized by lowercase m. All right, so please know the difference between molarity and molality in terms of the symbolism. And by definition, the molality of a substance or a solution is equal to the moles of a solute divided by the mass of the solvent expressed in kilograms. All right, so these are two different um, ways of expressing concentrations, and it's very important that you don't confuse either one of them, right? Molarity is the moles of solute per liters of solution, while molality is the moles of solute per mass of solvent in kilograms. So that's the difference, in fact, shown here. Molarity in the denominator of the equation, it gives you liters of solution. That's the definition, or that's in the formula. Whereas in the case of molality, in the denominator, you have the mass of the solvent expressed in kilograms. Okay, so here is an expression, or I should say an example, of a question involving what we just learned. So the question says, what is the molality of 5.86 m ethanol solution? And it gives you the formula, whose density is 0.927 grams per mil. All right. So first thing we'll, of course, write down is the equation for molarity. I'm sorry, molality, because that's what the question is asking for. So that's the expression that is given right here. So basically, what this expression is saying is that you need two things in order to determine the molality. You need the moles of the solute. Okay, why is my thing not writing? Okay, I'm sorry about that. You need the moles of the solute, and you need the mass of the solvent in kilograms. All right, so the other expression that we need to have is the molarity, which of course is the moles of solute divided by the liters of solution. So how are we going to get the moles of the solute? Firstly, well, what we can do is make an assumption, and the assumption is that we're working with 1 liter of solution. Now we can use pretty much any volume, but 1 liter is a nice round number because it simplifies things for us in that since the definition of molarity is moles per liter, then per every liter of the solution, there is 5.86 moles, right? Now, of course, we can convert from moles of ethanol to grams of ethanol using the molar mass, all right? So you should know to do that. Basically, what you're going to do is take the moles of ethanol and multiply it by a conversion factor, which represents the molar mass, where you have the mass in grams of ethanol, which I think is 46 grams, divided by 1 mole of ethanol. And if you do that calculation, you're going to get 270 grams of ethanol. Now, the question gives you the density, which is 0.927 grams per mil. Remember, we assumed 1 liter of the solution. So therefore, for 1 liter of the solution, which is equal to 1,000 mils, we can determine the mass in grams of the solution, which is 1,000 mils times 0.927 grams per mil, and that gives you 927 grams, which we can convert. Well, first, before we can do any conversion, what we do is that we need to find the mass of the solvent. Remember, in the definition of the molality, we need the mass of the solvent. So what we do is take the mass of the solution and subtract from that the mass of the solute, which is ethanol, which is what we have here, and that gives you 657 grams of the solvent, which we then convert to kilograms because we need that mass to be expressed in kilograms. And all we have to do from here is plug in the numbers for the moles of the solute, right, which is the 5.86 moles of ethanol, divided by the mass of the solvent, which is a 0.657 kilograms. So that's what we have here. And then that works out to be equal to 8.92 m, all right? And that's basically how we do this particular example. Okay, we're going to stop here for now. The next video will deal with the relationship between the solubility of a solute and the temperature of the solution.